So looking at combining functions that have different natures, a couple of quick definitions. Today we're doing adding, subtracting, then on Monday we'll do multiplying and probably dividing together. And then on Tuesday we do something a little bit different. So when you're adding two functions, you are literally adding the y values at the same x value. So when x equals 2, you add the y value of each function together to get the new function. So if you had a list of points, you would just match up the x's to add the y's, and that would be your new one. Or if you broke up, if you were given functions as graphs or something, you could just pick points off the graph, put them in a table of values, line up the x's, right? Pick your x's, find the y for each, and then add them together to get the next one. That's literally what you're doing. Okay? And then obviously same for subtracting. And multiplying and dividing for that matter when we get there. Okay? And one thing you need to know, that the new function, the domain on which it exists, is the overlap of the domain of the two previous functions. So if one of the functions doesn't exist somewhere, the combination function also doesn't exist there. Both functions have to exist in that part of the domain for the combination to exist, right? So think of the square root function, starts at 0 and then goes positive from there. If you're adding like a linear or something to it, you can't add something to nothing. It's not like you're adding to 0. There's nothing to add to because the square root function doesn't exist in the negatives, right? The parent function. So the combination wouldn't exist there as well. So if you're, a bunch of the questions in the practice ask you to find domain of the combination of when you add two functions together, find the domain of that new function. And so you have to think of what's the domain of f, what's the domain of g, and then now I can determine the domain of f plus g. It's wherever they overlap, wherever both exist. Does that make sense? Okay, so I just want to show a quick little, or bit of a little demonstration here to show you what I mean. The green function at the bottom, I hope you can see this. The green function at the bottom is what we're going to add to the red function. So if I look at this value, this is the distance. My y value, we know this, but it's funny how we don't always think about it this way. My y value is a measurement of the distance from the x-axis, right? So that point has a y value of 2.9, and it is that distance. Okay? So I'm adding that 2.9 to 4.5, which is the same x value. What is the x value in this case? I don't know, 8.6 or something like that. And so I'm adding it to 4.5. So 2.9 plus 4.5 is 7.4, and I can show that here where I take that distance and I add it, and it puts me on the blue curve, okay? And I do that for every point. So I take that and I add it, okay? And if it's bigger, notice how this space is bigger, so there's more distance between these 2 points, right? That space is bigger. This space is really small, and so that space is really small. Okay, I do that for all of these points. What if it's negative? Look at this. This is neat. So when I go down here, that's negative. And so notice that my blue one, which is the result of adding them together, is below the red curve there because I've added a negative value, right? Does that make sense? Okay, but that's the understanding of whoops. Okay, and so I've got all of these different points that I have, and let's get a small one, and I just add them all to get all the points of my new blue curve. Pretty easy to visualize when it's adding. A little bit trickier if it's multiplying. Same idea when it's multiplying, but it's a little bit harder to visualize. Okay, so let's try a question here. We're given two functions, f at x and g at x. Determine the equation and graph of f plus G and F minus G. First of all, I'm going to graph these. I only have one grid. I should have two grids. It's bad planning. 1, 2, 3, 4. Okay, so that one's G, and then F, negative x squared plus 1, so that's a parabola. Hopefully we're all really good at graphing that. Up 1, opens downwards. So I can do the same thing that we did in that demonstration where you actually look at the points and you add them together. For the first one, F plus G. So pick some key points and start adding them literally together. So if I go to like at 1, it's not very interesting because it's 4 plus 0. But if I look, let's say right about here, what is that point? It's about, I don't know, 0.75. And this one's about, I mean, I could calculate it, but maybe 1.75. So I add them together to get the new point. But we're also going to do this algebraically. So our notation is in brackets F plus G at X equals F at X, which is negative x squared plus 1, plus G at X, which is 4x. So that just works out to a new quadratic in this case. Now I'm going to quickly complete the square to graph this. X squared minus 4x plus 4 plus 4 plus 1. And I get negative x minus 2 all squared plus 5. So I go over 2 and up 1, 2, 3, 4, 5. And just watch for a minute because I know you're probably trying to scribble all of this down, but just watch. Think about this graph. I'm going to use a different color. Again, it has no change in its growth pattern. So I go over 1, down 1, over 2, down 4, 1, 2, 3, 4. Look at where these points land. As they should. This point is 4 plus 0. So it didn't move. That's where it overlaps with that graph. This point at the vertex here is 1 plus 0. So that's where this new one overlaps with that graph, right? So see how it is literally the result. Algebraically, I added and I was able to simplify and get a function that we recognize, that we know something about, a quadratic. It's not always that easy, but this is a nice demonstration of one where it works. So we know something about that algebraically. The algebra all fits. I literally added the two functions together algebraically. But adding the y values also fits and makes sense. Okay? Cool. B, F minus G, yep. F minus G, I hope you know, is obviously different from G minus F. They'll be related but different. Sort of related but different. So make sure you get that order correct. X squared plus 1 minus 4x. Okay, so I'm going to do the same thing and quickly complete the square. And graph this one. So that one goes over 2 up 5. Should have had 2 grids. It's a bit of a mess. If you don't get the whole graph all the way copied down and drawn properly, I don't think it's a big deal. Don't worry too much about it. You can graph that stuff. That's not a big deal. Watch this for a minute. So how did this point get up here? Well, my graph, here's my graph F, and I subtracted -4, which means I added 4, so it's actually up there, right? So again, it makes sense. When you're that demonstration we did of adding graphs is easy to visualize because you're adding space. When you're subtracting, it's a little bit different. It's a little bit harder to visualize. You could do it if you played around with it a little bit, but when you're subtracting negatives, how that impacts things, right? But otherwise, it's pretty straightforward. Any questions? So algebraically, if you can simplify it, then absolutely you do. And in some cases, that'll be helpful, depending on what questions are asking you to do. But keep in mind, you're adding y values, literally. Even if you're getting caught up in the algebra, keep in mind that that's literally what you're doing. Okay, a couple of different kinds of questions. Determine the domain of f plus g at x if f at x is log of x minus 3 and g at x is negative square root of x plus 2. Okay, so the domain of f is what? This is what we just finished. So in general, you need to know what a logarithmic function looks like. And then what's the transformation that's being applied? How does that impact the domain? We're just looking at domain, not range. And without graphing, how can I determine the domain of the new function? So what's the domain of this one?
The domain is x beyond numbers where x must be greater than 3.
Greater than 3. Right. Shifted to the right 3. Usually greater than 0. Good. The domain of g. Haven't seen a lot of square root functions in this course. Haven't seen them in a long time. Anybody remember? We talked about it a little bit already today. What would be the domain of that one? Yep. Greater than -2? Greater than or equal to, right? Because the square root function has a point at there, so greater than or equal to, very good. So where would these two functions overlap? So my actual domain the square root function g goes over 2, and it's got a reflection in the x-axis, so it opens down, so it goes something like that. And the log function is over 3, and so goes something like that. So they cross at 3, and g exists over here, but f does not. So the domain of the new one, this is what I was talking about before, doesn't exist there as well. So in this case, x is an element of the real numbers such that x is greater than 3. It's not always just the same as one of them, okay? Sometimes it's a weird combination of the two. Sometimes it is just the same as one of them. Sometimes it's kind of the same as both. And sometimes it's a different combination too. I can imagine if I had two square root functions, one that went like this and one that went like this. What would the domain of adding them be, right? You'd have to consider both of them and kind of put them together. Okay, determine the equation for f plus g at x. If f at x is same two equations. This is one where like you think, ooh, we're going to learn some cool math here. How do I add logs and square roots? Ooh, this is going to be powerful. Okay, so yeah, we'll just start by kind of writing it out. So log base 10 of x minus 3 minus square root of x plus 2. We start by just writing them. Like I'm subtracting because it's negative, but you're actually adding, right? It's pretty straightforward. And we're done. That's it. Because you can't simplify that any further. So sometimes these questions are a little bit weird where you just write them out. And that's it. But sometimes you can do stuff. So sometimes it does work out. And when we get into products and quotients on Monday, we'll see some interesting examples of that. But in this case, nothing going on here. Yep, that's the answer. We're done. Okay, one more. I think this is the last example. Okay, so we have two different equations, two different functions for f at x and g at x. And now it wants us to do g minus f. So remember when I said g minus f is different from f minus g? That's pretty straightforward. That should be pretty obvious that that's true. Is everybody okay with example 3? You got it copied down? And you understand you just write it. There's nothing going on there. So one note on example 3. What if you had to come up with the domain? That's easy. We did that. What if you had to come up with like a graph of f plus g? How would you do that? So in the textbook, you'll see you have to graph them both and literally look at the graph and look at the points like we did in that demonstration. Like this, I have to pick a point and pick another point, find their values, estimate their values, and just add them. Okay? And you'd get a rough idea of what the result looks like. Example 4, example 3. Determine the equation for g minus f. All right, let's do it. So G is 2x minus 5 minus bracket x plus 3 squared minus 4. However you want to do this, if you want to distribute the negative now or later, I think it's pretty clear. You're going to have to expand f so that you can collect like terms. You don't have to complete the square unless you're asked to graph it or something like that afterwards, right? If you're asked to graph it, then that's how you would probably do it. But one way or another, just to put them together, you have to expand all the terms and then simplify to get the result. Okay, so give that a try. Good practice of some grade 10 algebra. All right, negative x squared minus 4x minus 10 is what I got. Any questions?